Alright guys, so let's do number 61. Alright, so this is going to be a very interesting problem. An enemy ship is on the east side of a mountain island as shown in the figure 4.61. The enemy ship has maneuvered to within 2,500 meters of the 18 meters high mountain peak. It can shoot a projectile with an initial speed of 200 meters per second. If the western shoreline is horizontally 300 meters from the peak, what are the distance from the western shore at which the ship can be saved from the bombardments of the enemy ship? So anyways, folks, this is going to be, what I like about this one in particular is that this is really going to touch your knowledge base of the physics. All right, so how do you even solve this? Well, before I attempt to even set anything up, folks, let's kind of visualize like the equations, because those are going to be very important. And it took me a while for this to solve it, not because I couldn't figure out the equations, which I did, but it was mostly because the mathematics is a bit rough. And notice here, and when you look at this, you can see that there's two different angles. So realistically, if the angle is 0, maybe it's going to hit this part. It's not going to, it's just going to hit this mountain, and then it's going to go here at the peak, whatever, depending on the angle. And then it's going to go high above the mountains at some distance. We don't know the maximum distance, but we don't really need to worry about that. And then it's going to go back down to here. And then from there, once it travels low enough, it's going to hit back into the mountain. So I did graph this on Desmos just to confirm my answer. And even though I could have checked the solution manual, which I haven't, there are two different possibilities where this particular angle will match up this component. Well, anyways, all right, so let's graph this. So this is going to be the x-axis, and this is going to be the y-axis. And I'm going to put the y-axis right here, because this is going to be my setup equation. And the initial velocity here is going to be some b naught, which is going to be, which I'm going to write it here, is going to be 250 meters per second at some angle, which I'm going to call theta naught. And the distance here, according to my variables, I'm just going to put all in my variables, folks, is going to be 2,500 kilometers. And my height is going to be 1,800 meters. And I guess that's it, folks. So if you have some initial velocity, we know gravity is 9.8 meters per second square times the time. Well, there's your motion graph. All right, so before I attempt to graph this, let's write the variables that's given. So we have, now remember, this is not going to be part of the motion graph. This is just going to be something separate. So we're going to have this graph that's going to look some parabola shape. It's going to reach its maximum height, and it's going to go downward. We want the angle that it goes downward, because logically that's where it's going to be, the distance is going to be at. And this is where it's going to land. So, and according to this, we want this distance to be 2,500 meters, and we want the height here to be so basically, folks, this motion is going to look like this. You're going to have L is going to be some vector that's going to be in terms of x and y, and we want the specific height. And notice that I'm taking my time to solve this problem, folks, because this problem is a bit hard. So how do we solve this problem? Well, The first step is to let let x be the distance d, and my y to be h. And now this is going to be the picture. I'm going to get this out of the way. And your setup, it's going to look something like this. We want to define t naught to be the time it takes for this object to be here, and some t, and you want the t1 to be the time it takes for this object to hit that point. So we want to be a little specific, folks. We want to say that the time it takes for it to reach 2,500 meters is this distance d, which is going to be v naught cosine of theta naught times t naught. So, and we want the height to be h, and we want the y to be h at the distance v. So this is going to be theta naught times t naught minus gt squared over 2. Now, I am not going to do the mathematics for you guys, but I'm going to give you the end result. What you want is you want to solve for t naught. So you're going to say that t naught is going to be d divided by v cosine of theta, and you want to plug it in here. And in the end, you're going to have the I kind of changed this around when I did that. So, but the end result here would be g d squared over 2 v naught squared times tangent square of theta naught plus d times tangent of theta naught minus h, and I think I already, no, it's fine. It's all right. So g d squared 2 v naught squared times tangent of theta. I just got to add this little extra piece, g d squared over 2 v naught. Now this is a simplified version, folks. This is what I have in my notes. And you want to use the quadratic formula on this one to get your two angles. Now the angle, I'm going to define that to be theta h and theta l, because that's actually very important. So let's get what those two angles are, and I'm going to put this in my calculator. And the two angles here, according to what I have, and I have my calculator, so I'm looking at my calculator here, folks, and the angle here is going to be, let me think about this, the shortest angle would be theta of L, so that's going to be 50.1 degrees, and the other angle is going to be 75.6 degrees. Beautiful. All right. Now, this is important, folks, because once you get that angle, and yes, there is a process involved in this, which is using the quadratic formula and taking the tan inverse to get to those two angles, because there's really two solutions to this, to that particular equations. Your maximum distance x is going to be, so what's the theta naught? So theta naught is going to be this angle right here that I'm defining. So we're going to let theta naught be 50.1 degrees, and I actually have that stored in my calculator. If theta naught equals theta of the larger angle, then x here would be 6.28. So if theta naught equals theta of L, x is going to be that many kilometers. Now if we let that theta naught be theta of h, then your distance here is going to be, so X is going to be 3.07 kilometers. Anyways, we're practically done, folks. So all we need now, the question is asking if the western shoreline is horizontally at 300 meters from the peak, what are the distance from the western shorelines? Anyways, so in order for the ship to be safe, this would have to be approximately 270 kilometers. All right, I hope this helps.